Feeling like a couch potato these days. Okay, more like a computer chair potato. But since I want to try to record this video in one full swoop without having to edit much, I should probably start messing around. So let's get started. Today's topic is nth roots. So we're going to take the root of something, which means we're going to go backward. Instead of cubing something, we're going to find the cube root. Instead of putting something to the fourth, we're going to take the fourth root. So for example, if you look up here, we have these powers, x to the third equals 64. We know that 4 times 4 times 4 equals 64, so 4 is the cube root of 64. Okay, you guys can see those examples there. The fourth root of 625 is going to be equal to 5. The fifth root of 32 is 2. Okay, so however many factors of some number, so n factors of a, if that equals b, then you can take the nth root of that and get that factor, so you can get a. So here's another example, because -3 to the fourth, and I've already highlighted this, -3 to the fourth equals 81. That means -3 is a fourth root of 81, and 3 is a principal root. We'll talk about that here in a second. This symbol indicates the nth root. The n is considered the index. That's the radical sign, we know that, and then the radicand is the number that's underneath the radical sign. So for example, some numbers have more than one real nth root. We've talked often about taking the positive and negative version of things. So 64 has 2 square roots, 8 and -8. When there is more than one real root and n is even, so 2, 4, 6, you guys know those numbers, the non-negative root is called the principal root. So here's some examples. The square root of 25 is 5. Negative square root of 25 is -5. And then we have plus or minus square root 25 equals plus or minus 5. So the principal root would be the non-negative side of it. The definition of real roots. So we're going to have some roots that may not be real. If we have the radicand as a, if a is greater than 0, we're going to have one unique positive and one unique negative real root. So this is like, for example, the 64. So if a is 64, we have +8 and -8. If a is less than 0, we're going to have 0 real roots, because we can't square a number and end up with a negative. 5 times 5 is always +25. -5 times -5 is always +25. So if that number in the radicand, or underneath the radical, if the radicand is less than 0, then we're going to have 0 real roots. If a equals 0, we're going to have one real root, which is just 0. 0 times 0 is 0. So there's some definition, there's some examples of roots. We're going to get into our examples here. If you guys want to pause this slide and take notes, or if you guys are following along in your textbook, I'm going off of page 293. So example 1 says to simplify, and it gives us a lot of radical expressions. So what we want to do is we want to first pay attention to what root we are taking. So if it's unlisted, if there's no number in this little area of the radical, then we have, it's just going to be a square root. So we're finding the square root plus or minus square root 16y to the fourth. So what we're going to do is we're going to find the square root of 16, which is 4, and the square root of y to the fourth, which is y squared. And since it was plus or minus, we're going to have plus or minus 4y squared. Not all of them are going to be that simple. So let's look at this next one. We have a negative, which we're going to have a negative on the outside of this next part. And we have this whole expression here, this whole chunk is to the 8th power. So we have x squared minus 6 all to the 8th power. So what I'm going to do is, if you guys can imagine that this piece is just one thing, let's substitute, okay? So I'm going to say x squared minus 6. Let's say that equals y, because now I have something that looks like this. And I'm just going to do a little bit of side work, kind of show you guys where I'm coming from with this. So we have y to the 8th power. So if I were to take the square root of y to the 8th, I'm looking at pairs because I'm talking about square roots. So pairs, how many pairs of y's can I take out? So I've got this kind of thing going on. I have y, 2, 3, 4, 5, 6, 7, 8. And then I'm going to look at pairs. I've got 1 pair, 2 pairs, 3 pairs, 4 pairs. So if I were to take that outside of the radical, and if I'm just talking about y still, I would have a negative y to the, and since I have 4 pairs, it would be to the 4th. So if I take that information and go back to my x squared to the negative, or x squared minus 6, that's what I'm going to end up with. I'm going to have, x squared minus 6, and instead of to the 8th, it's now to the 4th, because I'm going to have 4 pairs of that chunk, of that whole piece. So this is going to be negative x squared minus 6 to the 4th. Box that one. What just happened? You guys didn't see that, but like something like my pen scratched on the thing. I think I need to get a new pen tip or something. Don't fail me now. I'm trying to do this without having to edit. Okay, part C. So there's a lot going on in part C. We've got 3 different terms that we're talking, well, not terms, 3 different parts. We've got coefficient, we've got an A, and we've got a B, but we're taking the 5th root now. So what we're doing is we're finding groups of 5. So I'm going to look at 243 and I'm going to think of, is there any certain number that when I multiply it by itself 5 times is 243? So if you guys do some calculations, you guys can even like get a calculator out for this part. Find the 5th root of 243. I'm going to find out that 3 times 3, 5 times, okay, that's going to be 243 because this is 9, this is 9, this is 81. 81 times 3 is 243. So the 5th root of 243 is going to be 3. Now, oh shoot, I need to find how many groups of 5 I have in a to the 20th. So I could do like that last example. I could write out 20 A's and groups of 5. But what I'm just going to do in my head, I'm going to say, okay, 20 divided by 5 is going to be 4. So I should have 4 groups. So this would be a to the 4th. And then I have b to the 25th. If I divide that by 5, 25 split up into 5 groups is going to be 5 left over. Ooh, that's not a 5. So part C is going to be 3a to the 4th, b to the 5th. And we're just going to leave it positive. It's the principal. All right. Next one, part D. So part D says the square root of negative 16x to the 4th, y to the 8th. So here's the issue. We have an n that is even. So that means something times something equals this negative 16. We talked about it on the last slide, the last page, that we cannot take the square root of anything negative. So this one we would have no real roots. So no real roots. Okay. We can still simplify it though. We have the idea of the I, because remember I equals square root of negative 1. So if I were to find the square root of negative 16, it would be plus or minus 4i. And then if I were to find the square root of the other 2 things, square root of x to the 4th is x squared. Square root of y to the 8th is y to the 4th. So your roots are 4i x squared y to the fourth, and negative 4i x squared y to the fourth. But it is important to note that there are no real roots here because n is even. Okay, so this next part is talking about focusing on the principal root. So whenever we take the even root of an even power and the result is an odd power, we are going to use the absolute value of the result to ensure that the answer is non-negative. I know that sounds like, what the heck did you just say? But let's look at these examples here. We've got the fourth root of y to the fourth. And if you take the fourth root of y to the fourth, you're going to get just y. However, technically, we don't write it, but it is y to the 1 power. So what we did here is we took an even root of an even power and we ended up with an odd power. Okay, so this is a scenario where to ensure that the answer is non-negative, we would put it in absolute value. So instead of just y, we're going to talk about the absolute value of y because we're looking for that principal root. So for example, part B, I'm going to just focus on taking the sixth root of all of these pieces here. So I'm taking an even root. Okay, I'm going to focus on the 64 because it doesn't have anything else going on with it. So the sixth root of 64 is going to be 2, and we can just leave that standard. But then we've got this chunk here, this x squared minus 3 is all to the 18th power. So if we're taking the sixth root of something to the 18th, 18 is also even. So this is one of those scenarios where we would use absolute values. So just like before, how I kind of substituted, this could be y to the 18th. And if I were to take the sixth root of that, that would give me just y to the third. So in this case, my y is x squared minus 3. So times x squared minus 3 to the third. However, again, because I took an even root of an even power and I ended up with an odd power, I ended up with 3 as my exponent, I would use absolute values around this piece right here. So the simplified version of that is 2 times the absolute value of x squared minus 3 to the third. And I've actually decided to do 2 more of these. I'm going to do example C and D. But let's look at example C as the square root of 36 y to the 6th. And then D is fourth root of 16 times x minus 3 to the 12th. Okay, so it looks like we've got a lot of even roots and even exponents here, even powers. So what I'm going to do on part C is I'm going to take the square root of 36, which is just 6. All of these numbers, all of these coefficients, you don't need to worry about the absolute values around those because square root of 36, 6. Because we're focusing on the principal roots. So y to the 6, if I take the square root of that, this is like a 2, and I always like to just divide those two numbers. So y to the 6 divided by 2 is 3, so this is going to be y to the third. However, it's an even root to an even power, so we're going to have absolute value of y to the third. Okay, part D, we're going to take the fourth root of 16. So the fourth root of 16 is just going to be 2. And then we've got the chunk x minus 3 to the 12th. We're taking the fourth root of that. So 12 divided by 4 is going to be 3. But again, I'm ending up with an odd power. That's my result has an odd exponent in it. So even root, even power ended up in an odd power. So that's where I would use my absolute values. So 2 times the absolute value of x minus 3 to the third. Okay, and that is going to be what we do. I'm skipping example 3 in your textbook, so if you're following along with me, we're not doing that one. But that's looking into nth roots. of radical expressions. You guys have been doing great with asking questions, so please continue to do that. Have a good day.